you guys had done for me is you had taken little cards that match and you had them flipped over and you played the memory game. This has to do with Hess law, and I'm going somewhere with it. We had a lot of love last period, kind of making sense of all this. So on number 1, when you play the memory game, what do you do when you make a match, Kat? Yeah, when they match up, you pull them out and you set them to the side. And so let's just pretend that maybe like the thermometer card that matches the thermometer picture, like maybe you only have one of those. What would end up happening to that card? Jaleel. If you were playing the matching game, you don't have a match. What do? You just leave it so it never comes out and goes in a pile, right? It stays on the table. And so that has to do with Hess's law, and that's what we're going with. So let's go ahead and get started. Yesterday we had talked about one of the ways to do the enthalpy of reaction. And so today we're going to talk about the other 3 ways to do it. Not very equitable, but it is what it is. So starting at the beginning, like I said, this is on Schoology under Thermodynamics 2 lecture. The practice and the lecture are backwards in the order, but I mean you can read, so you're fine. Everybody have this pull up that wants to follow along. All right. So calorimetry is probably the most straightforward way. Remember yesterday there is no formula for that. When you make a bond, it releases energy. When you break a bond, it takes energy. You get the numbers, you add them up. Number 2, though, is using a calorimeter. On Monday, when we do the lab, we're going to be doing calorimetry. And so it's important that we understand this. So calorimetry, we're going to measure that heat transfer. And remember, you can't measure heat directly, so you're going to have to do that by getting the change in temperature. So heat flow cannot be measured directly. We measure it by taking the temperature before and after. And with thermodynamics and thermochemistry, we don't have to use Kelvin because all of these are going to be, because we're doing heat transfer, we're going to have a temperature change. A degree in Kelvin is equal to 1 degree in Celsius. I don't mean 1 degree Kelvin is 1 degree Celsius. I mean that if I go from 42 to 43 Celsius, that is the same as going from whatever that is in Kelvin to 1 more degree Kelvin. Mental math is not with me right now. You'll see why at the end of this I can't do math in my head because I'm about to tell you a lot of stuff. So anyway, John formula, no problem. So this formula is on your formula sheet. The specific heat capacity, this is really important, okay? A lot of conceptual multiple choice questions come from this. A specific heat capacity is like a pocketbook, all right? Now let's say Granny's got a pocketbook right here. Granny's got a new micro course. Right? What? There you go. Granny got some money, I guess. Anyway, specific heat capacity is like a pocketbook. Okay? If you have a big specific heat capacity, you can hold a lot of heat before that heat starts to spill out. Guess what happens when heat spills out? Like you can't hold it. The temperature changes. See what I'm saying? So if you have a big specific heat capacity, like water, 4.184 joules divided by grams times degrees Celsius, that's huge. Most metals are less than 1. Okay? And so water can hold a lot of heat before it changes temperature, which is why sometimes but to make spaghetti. And I know if y'all took AP Environmental, I was going to say, it's hard to heat cool water because it has high specific heat capacity. That's why places on the coast have a temperate climate. That's what I was talking about. Water has a big pocketbook. Alright? Now, if we have some metals, you think about it, you try to heat up some iron, throw iron in the fire. Yeah, it's going to heat up like that fast because it has a little pocketbook. It's got like a wallet. It's got a wristlet, okay? It just heats up right there. All the girls got it. And the boys are laughing too. That's awesome that the boys are laughing at that. So anyway, it doesn't take much energy to change that temperature because it can't hold a lot of heat before it changes. And so this Q is basically, those are the same because we're under constant pressure and volume. So for us, for thermochemistry, that's that heat and enthalpy are the same. You have to understand in physics that's not true. Okay, but we're not in physics, so we're cool. Anyway, that's the mass, and that's the C. The C is specific heat capacity. Sometimes you'll see it written like that, like a C and a P. Same thing. Delta T is your change in temperature. So again, sometimes you'll see this as a C. Sometimes you'll have it as a K. Don't matter, it's the same. Anyway, so remember, temperature change or change in anything is always final minus initial. If you're doing percent change, it's final minus initial over initial. in your head, do I haunt you with these things I've said before?
Yes.
Yes, I'm really sorry. But it is what it is. So y'all good there with specific heat capacity, how much heat you can hold for your change temperature. No problems. All right. So this is what you're going to be using on Monday. You're going to have a coffee cup calorimeter, and I actually have like some high-grade styrofoam calorimeters. They're like $12 a piece or something. I mean, they're really nice. Got them from a grant. They might have just been $10, but that's a lot for a styrofoam cup, my friends. So they're very insulated, and they do well. And so when we're doing this, basically you're going to have a reaction happening, or like I said, like we're going to put sodium carbonate in here, and then it'll change temperature. So your sodium carbonate is going to dissolve, whatever. That is your system, the sodium carbonate that dissolves. The surroundings include the water that it's happening in. Is the water taking place in, is it part of the reaction? And then the calorimeter itself is the surroundings. So, oops. If I'm using a coffee cup calorimeter, like I said, we're going to use the solution as the basis. So again, that's our heat. The Q is the heat. Now the mass of the solution, this is really, 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 really important. 1 milliliter of water equals 1 gram. So if you have a 200 milliliter solution, if I want to convert that to grams, 200 milliliters is 200 grams. And you don't have to necessarily show that. You can just put a G on it, but that's why. Like that's where that's why the metric system is beautiful. Yes.
That's just water.
Yeah, that's just water. Like that is where we got like a cubic centimeter is a milliliter, and that's a gram. Like they did that on purpose. Okay. And the specific heat of water is 4.184. Sometimes you'll see it as 4.18 instead of 4. Do whatever number they give you. Sometimes they round off, sometimes you don't. Yes, sir. Can you say that again? Yes, yes. And so when we do the lab, we will be using distilled water. But on the AP exam, they're going to like if we put the sodium carbonate in here, like we can assume that even though it has ions in it, we can assume that the specific heat capacity is still 4.84. And we can assume that the coffee cup doesn't absorb any heat. Those are assumptions that will always be made here and on the AP exam, and I've checked, I'm sure. So anyway, and then the change in temperature, remember, final, last, initial. So, moving on. Remember, like I had said, the reaction itself is the system. The water that it's sitting in is the surroundings. The coffee cup surroundings, the universe is surroundings. But the water is the surroundings in this case. The heat or loss or gained by the solution is equal to that loss or gained by the actual reaction. So this is a bunch of hot mess. Let me just go back a slide. I don't even want to read that. Listen to me. Boop, first picture. Let's say that the reaction that happens in here, let's say that your coffee cup is hotter than when it started. Like the water in the hot coffee cup is hotter than it started. What kind of reaction happened in that coffee cup? Exothermic. So what is the enthalpy value? It's a negative. You have to just use your head. Don't try to, it's confusing. In the book, it was talking about, oh, Q and equals negative Q, blah, blah, blah. There's like 3 paragraphs on it. Just use your head. If inside the coffee cup it got colder, then the reaction was endothermic. And then the enthalpy of the reaction was positive. Okay? You don't have to, the issue is on that formula sheet, it just has Q, mass, specific heat, temperature. It doesn't get that negative. You have to use your head. And you have a head, and it's fine. I'm showing you how to do that. So what I was saying was, if that water, in this case, that water got hotter, it gained heat, then, well, guess what? The reaction lost that heat. So that's even confusing in a sentence. Could you understand what I said out loud? Then go with that. All right, so here we go. There's kind of 2 kinds of calorimetry questions. They're both on the AP exam a bunch. This is a favorite topic. Okay, it wasn't even hard for me to find a calorimetry question for your free response. The 2 free responses that you can look at in advance are gas laws. The one that you don't see in advance is calorimetry. You try to go through all the AP exams and all the calorimetry ones, you're going to be there for hours. So might as well just understand. How about that? Right. So anyway, there's 2 kinds of calorimetry problems. There's one where you're going to take a hot piece of metal and throw it in water. Okay? And then there's another kind, that's what we're going to do on Monday, where we just do a reaction in a cup. The kind where, like on this example, example where you're putting some metal in water, you're going to basically have to do two problems here. All right, so let's kind of read through this and I'll talk you through it. A 97-gram iron bar was heated to 143 degrees Celsius, placed in a coffee cup containing the water at 25 degrees. So the maximum temperature of the water was measured to be 28.4. Here's the deal. Let's talk about this. The iron is going to go from 143 to 28.4. Yeah? The water is going to go from 25 to 28. Okay? Water has a specific heat capacity of 4.184. Iron, we don't know, is asking the heat gained by the water and the heat lost by the iron. These should be the same numbers, different signs. Conceptually, you follow. The specific heat of the water. Do you see how these are two different substances? So guess how many times I'm about to have to use that formula? Twice. Because I have two different heat capacities, two different temperature changes. So it's kind of intuitive. Yes, sir?
Are you going to memorize the
No, they'll give you that. And you'll know it by the time you're done. But so let's go ahead and I'm going to switch screens over. If y'all can kind of, this is when you have two different substances. I mean, the answer to everything. Don't look. It's okay. I got y'all. When you have two different substances, I'm actually going to do water first because we had all the information for the water. Make a chart and do the water on one side and the iron or whatever it is on the other side. Or just do whatever you want and ignore me. But this is what I do. I have all the information I need for the water. The heat gained by the water, I don't know. I can solve for it though. The mass of the water, how many milliliters of water is that, y'all? 150?
300.
Oh. 0.0? So that's grams, right? So Q equals, there. So that's the mass. The specific heat capacity of water is 4.184 joules over grams times degrees Celsius. And then the temperature change of the water, it went from 22 to, no? I'm saying where did it start? Oh, okay. So 25 to 28.4. Alright, so remember it's final minus initial. So 28.4 degrees minus 25 degrees. And so when I do that, I get 3.40 degrees Celsius. And so that's easy, right? We can do that. There's no problems. No, I said that. So the thing is, with thermodynamics, you're going to do Celsius because it's always temperature change. If you change it to Kelvin, let me ask you something. If I change this to Kelvin and I add 273 to that, and I add 273 to that, that would be, just go with me. That would be like saying add 100, add 100. If I add 100 to 100, that would make 128, that would make 125. Am I going to get the same answer? Yeah, don't do that. It's a waste of time. You don't change this to Kelvin. That's only gases, okay? And there's some stuff later where it comes back, but no, this is fine. So anyway, push buttons on your calculator. La la la. I ended up getting I got 3 sig figs, so 3. Excuse me, not. I'm just making up some numbers. Is this what you guys got? And look at my units: grams, Celsius, joules. Happy times here? So the question said how much heat was gained by the water. Water is gaining heat, so should this be a positive number or a negative number? All right, think about money. If you gain money, it's positive, okay? Like your little penny I gave you. So if I'm solving for the next part, obviously the heat lost by the iron, if it's losing heat, it's negative, right? It asks me to solve for the specific heat capacity of iron. So let's think about our formula. Q, specific heat, and delta T. Q is negative 4,980. that's joules. The mass of the iron, was it 97 grams? Alright, so 97 grams. And then the specific heat of water is, I don't know. And the delta T is pretty high. It was, it ended up at that 28.4, but it had started out at 143. So the final is the 28.4, right? And the initial was 143. So 28.4 minus 143. Negative 114.6 degrees. Well, this is algebra from here on out, right? Got to isolate my variable, which is my specific heat. So I'm going to divide both sides by 97 times the temperature. I don't know if I've ever written 4 ones in a row before. That's pretty fun. So 4,980 by the answer. So I like how my units work out, right? I have joules on the top. I have grams and degrees Celsius on the bottom because I divided by grams and the temperature change, right? And I can only have 2 sig figs because the mass is given to me in 2 sig figs. And that's it. And we would expect a metal to have a specific heat capacity less than 1, and we do. How does that make you feel? Not so bad, right? Happy times. Alright, I'm going to let y'all try one of these in a second, but there's another kind of calorimetry question, and that's where, this is more common kind, where you can do a reaction in a cup of water. And so let's kind of go through that. The next kind is the kind that's in your lab on Monday. So this is pretty important. Oh, and by the way, if you didn't, like if you messed up on your signs or whatever and you got a negative heat capacity, then you would know you messed up because it should be a positive number. So there's all the work. I did it, but I did it different. This just looks terrifying. Like, right? Like, I just can't. Anyway, this just looks awful. So let's look at this. Let me read it to you. When 20 milliliters, so as soon as I read that, I'm like, okay, 20 grams. 20 milliliters of 1 molar sodium chloride is at 22 degrees. It's mixed with 20 milliliters of 1 molar silver nitrate at 22 degrees. In a calorimeter, a white precipitate forms. In your head, you should be like, oh, that was silver chloride. Yeah. And the temperature of the mixture reaches 29.6. Assume that the specific heat capacity of the mixture is the same as water, and the density is the same as water. That's very common. That will always be like that. And you can always assume again that the calorimeter doesn't absorb any heat. So that's cool. So write a net ionic equation. Should be able to do that pretty quickly. So if I have sodium chloride and then silver nitrate, that's going to give me silver chloride and sodium nitrate, right? I'm going to run out of room, but I think it can work. And that's a solid. The silver chloride is a solid. So, you know, when I graded your last FRQ, some of you guys had trouble writing the net ionic equation. You run a net ionic equation. Look for whatever went into making that liquid or that solid. And so the only 2 things that went into making that solid, the silver chloride, is the silver ion and the chloride ion. So the net ionic is silver plus chloride, and these are aqueous. Aqueous. Gives me silver chloride solid. That's a net ion. Any problems with that? Then it's asking for the enthalpy for the reaction. Now let me tell you something about an enthalpy for a reaction. That's always going to be in kilojoules per mole. So what we're about to have to do is we're about to have to figure out how many moles of silver chloride was formed. Right? So when I say per, what does that mean? 5. So kilojoules per mole, we're going to do the calorimetry thing to get kilojoules. And then we're going to divide by the moles of silver chloride. And can you find moles of silver chloride from all that information up there? Yeah, you sure can. And we're going to use the BCA table to do it. Yay, happy time. It's fine. Everything's fine. Hush. You didn't say anything. I saw your faces. Alright, so 20 milliliters of 1 molar of each. Okay, here we go. So I'm going to go back to the formula. Q equals, and you know how I can remember this? Because, yeah, you have a formula sheet, but there's questions on the MCAT. See it? I told you that already. Yes, sir. That's only if chlorine's by itself. So the diatomic elements with bromine and iodine and all those, they're only if they're alone. So in their all the Brinkelhoff elements, or most of them are gases, but like if chlorine is in a compound or whatever, you just do the balancing of charges. That answer your question? Okay. So heat is equal to the mass of all this. Was it 20 milliliters of both? So what's the mass, y'all? 40. How many decimal places did it have? 2? Oh, okay. So just 1 decimal place. Thank you. Okay. So 40 grams. And then it said I could assume the specific heat capacity is the same as water. Oops. And then the temperature change, it went from 22 to okay, so 29.6 minus 22. So 7.60. Yeah. That's not the worst thing that's ever happened to me, right? So hit the button on your calculator. So what I have here is I have 1271.94. And I'm not done here. I'm not finished, so I'm not worried about 6 weeks yet. And that's joules. Now remember, the whole point of this was to find the enthalpy of the reaction, which is in kilojoules per mole. So if I want to make this kilojoules, 1, 2, 3, 1.271. That's good. Kilojoules. Now, how many moles of silver chloride were made, right? So that's a fun little thing. Here's where my net equation comes in. Silver plus chloride gives me silver chloride solid. So to find the moles of silver and chloride, this is a perfect stoichiometric ratio. I can tell that, you know why? Because it's the same, and then it's a 1-to-1 ratio. It's not always like that. So don't get used to that, okay? Anyway, so I had 20 milliliters. If I want to go to moles, y'all know how to do that? 20 milliliters of each. And it was 1 molar, so that's 0.0200 liters. And that's of silver, that was the silver nitrate, but I'm really only concerned with the silver ion, right? And then it was 1 molar, yeah? 1 mole, 1 liter. So I started out with 0.0200 moles. And these numbers for the chloride were the same, weren't they? Same numbers, so same moles. Minus x, 0, 0. 0 plus x, 0.0200 moles. So that's how many moles I made. That stuff we did last unit never goes away. Can you tell? Never. None of this ever goes away. We'll come back to this again in unit 9. Maybe it's just this course. Y'all good with my little table? Remember how to do that. the definition of enthalpy of a reaction is kilojoules per mole. So kilojoules per mole, and all I have to do is just be like 1.271 kilojoules divided by the number of moles I had. And then that's all you got to do. And then you get an answer. So and so I got, and how many sig figs can I have? It's like 3. 63.6 kilojoules per mole. Cool. That's the second of the 4. So what I want y'all to do, I don't want to keep going just through this and plowing through because you'll be like, what? Take a second and go ahead and do number 1 and 2 from your practice problems on the Schoology, and make sure you understand it. Alright? Then I'll keep going with the other 2 kinds. If you don't have your computer out, I'll pull them up for you. Or for the people watching at home. Lucky dogs. I feel bad for them. Do y'all feel bad for them yet? Like already, do you feel bad for them? I'm sorry if you're not here. There, so go ahead and try out numbers 1 and 2. On all these, is the energy going to be conserved? Are they? Or did you want to answer that 12 times? Is the energy going to be conserved on all these processes? Will the joules loss equal the joules gained? Did you want to write that 12 times? Sure? Skip all this. Skip all that. You got enough to do. Okay? You're fine. You have enough things to write except writing that over and over again. So try out number 1 and 2, and of course I'll go over it. Beaker 250. What's the battery life on these? Couple hours? Is that alright? 2 hours. 2 hours? Well, you got me in the middle of the day, so that helps. Alright, so do the thing, children. Ooh, on that last one that I just did on the board, I think I messed up. No, it's not a big deal. Watch. Hang on. I just remembered something. When we did this, the water went up in temperature, didn't it? Yeah. So the actual reaction that happened in the water, guess what? What's the enthalpy per mole? Is it positive or negative? Right? Be careful. I'm walking around if you need me. I'm going to put the answer for number 1, but obviously don't look up there until you're done. There you go. Then I'll put up number 2 here in a minute when I feel like we've had time to look at it. You had any trouble? Yes, Abby is making me happy. She's making the chart. She did the water on one side and the other one on the other side.
copper on the other side, I should say.
Yay. It's gonna be forever immortalized on YouTube. So or the copper or the water or the copper is a different. Every substance has a different specific capacity. You're either given it or you have to solve for it. You shouldn't have to be charged for that. That's for later. That's for the other kind of fluid. They wants to be a chemistry major, by the way. You got that. You good one. How's everyone going? Going? You put coffee instead of water. I mean copper. That's all. Man after my own heart. So you use the temperature change for the copper, use the additional one's not always relevant. Copper is temperature going down, not up. So then that was negative. And did you notice change the sign of the key value then when you solve because the loss of the Did you start with that?
Oh, when I put it in my calculator.
Well, let's see what we thought. You got the first part going? See, it's some good stuff for number one. Yay. That bit looks like a good thing. You did it. How's that number two though? straightforward, and then remember to use a BCA type of kind of mold. You're looking for molds of water. Okay, step on 2 yet? Did you get your Q value? Did you get the Q? Go do that first, and then you're going to use the BCA table to find molds. And you're going to take the temperatures from the Q, use the formula, divide by the mold. So, the number 2, looks like the mass is going to be 200 grams in unit. Specific heat is the same as water. And the temperature change goes from 22 your moles and stuff is going to be 0.1. So number 2, start by getting your Q value for the reaction. And the reaction is the well, if it was 1 molar. But there could be a time you guys need me to kind of quietly work out number 2 on the board? Okay. I'll start the process. On number 2, like you should be able to find that Q value, yeah? No problems there. Number 2, just a neutralization reaction. Hydroxide make water. Alright. So Q equals, I'm just, if you're working on number 2 and you're happy, then you do your own thing. I'm working it out here if you don't listen. It was 100 milliliters and 100 milliliters, so that's 200 grams. And then mass and then specific heat capacity is the same as water. And then the temperature change was at 28, it went from 28.2 was the final and the initial was 23. So 28.2 minus 23. Just take the time to show your work here because you never know. So delta T equals that. 5.2 degrees Celsius. So now you push buttons. And what is your Q value? Equal to here. Look at me and say it, Devin. And then did I mess up? So is it this number times 2? Yeah? Okay. JK. And so that is joules, and so I'm gonna need that to be kilojoules, 4,300 kilojoules. Now, this water, when a neutralization reaction occurred, this is the water. The neutralization reaction occurred and the water got hotter. So the water gained by the water, by solution. So negative kilojoules lost. Or I don't need both of those. That's the same. For delta H, right? That's what I'm trying to say. Now, like I said, enthalpy of reaction is kilojoules per mole, and so the Nadah equation for this and this is the same as, like what we're doing right now is the same as your pre-lab. This is the same as your pre-lab number 1. On your lab, it's not a perfect stoichiometric ratio. This is, and so you're going to run out and everything's fine. They were each for 100 milliliters. 100 milliliters of your acid is 0.1 liters. And then they were both 0.76 molar. And the definition of molarity is moles divided by liters. So I have 0.076. Is that how that math works? Okay, moles. And they were both the same. And so I'll start with 0.076 moles of hydrogen ions, 0.076 moles of hydroxide ions. And started with this is none. Add one of those, minus one of those, minus one of those, 0, 0, and I make 0.076 moles of water. The definition of the enthalpy of reaction is moles divided, is kilojoules per mole. So my kilojoules per mole then, remember my kilojoules were here. There's my moles of water. So if I put that here, I'm just going to write it in the middle because I ran out of room. And when I do that math, divided by 6, I get negative 57.2. And I can have, my sig figs, I was a little stingy with it. Well, it was 0.76 molar, so actually that's right. So 57 kilojoules per mole. So it's basically taking something you already know how to do. You know how to do the BCA table. And it's just add on to that Q equals M. This is the heat delta. That just is going to keep happening. Right? You just keep adding stuff. So anyway, y'all good there? And it makes sense it's negative because the water got hotter. So this has to be exothermic. Good times. Just so I can stop talking for a minute, why don't we go ahead and take this answer key, huh? Why don't we go ahead and do that? Because you're going to do all these except 15, 16, and 17. Of all the things we covered so far, this is the most heavily tested. So this is not something we can just, oh, we don't need to know. Oh, yeah, we do. So go ahead and get your little phones out, and then I'll let you tape it, and then we'll keep talking. We're 48 minutes into this. I know, right? You guys in the back good? You already know the answers? Cool. Oh, you're so awesome. All right. On your mark, get set, go. Oh, okay, I'm just kidding. Take snap. Oh, it's not happening? Okay. It'll be here on walkout period and after class and all those. Energy equals conserved. The heat loss is the same as the heat gain. It just keeps saying that. So, yeah, don't worry about it. All the heat loss is the same as the heat gain. Okay, this is where it starts getting real fun right through here. This is where you got to start singing to yourself. Not this. Just look at that. Okay. I'll show you how to do this, and it's okay. You're okay. And so 15 through 17 you can skip. And there you go. Yay. All right, back to work. Not that we stopped, really. All right, so we did this already. Like we had just said, the heat loss rate in the experiment that happened in the calorimeter, that's, you know, when we do the enthalpy of the reaction, we're going to do kilojoules per mole. We're going to have to do the BCA table and work that all out. So that's the first two ways. These last two are actually really easy to me, and I want to explain them, and you're going to be okay. So Hess's law is kind of fun. I actually enjoy Hess's law problems, and for whatever reason, when I worked this out last period, everybody's like, "Oh my God, my life makes sense." I didn't realize it was that confusing. So anyway, when you have a series of steps and you have to combine them to make that overall reaction, it's like playing the matching game. So let me show you. And again, y'all, I think you understood if you flipped it around, you had to reverse the sign. Like, you got that, but you just didn't know what to do. So anyway, let me show you how to, so just stop what you're doing and just watch me, okay? This is my target, okay? This is what I'm shooting for. When I get done, I want to pull out everything that matches from the reactants. So what I'm saying is, if I have like something on this side of the reaction and something on this side of the reaction, I can pull it out and it's no longer in there. Just like when you're playing the matching game. So let me show you. What I do when I do these, I know on the reactant side I need some NO2. I don't have any NO2 on the reactant side. So I know right now, before I even start, that this second reaction has to be reversed. I have to do that. There's no way to get around it, okay? So I'm going to go ahead and just rewrite that one. So, and then also, how many NO2s am I going to need? So not only do I know that it has to be reversed, I know that it has to be multiplied by 2. Is there any other way that I could get that 4 there? No, there's no way. So this one is, I'm going to reverse it, and then I have to times it by 2. So that means I'm going to times it by -2. Are you okay with that? I mean, I might have to do other stuff to it, but that so far is what I'm doing. So I have 4 NO2, and it does matter if it's a gas and stuff, but just for sake of room, I'm not going to write that. And I'm going to kind of line it up like in math class, right? Like I'm going to line up my, not decimal places, but I'm going to line up my yield signs. And then that gives me 4 NOs plus 2 O2s. All right? Now, that takes care of my nitrogen dioxide. My oxygen gas, I have some oxygen coming over here and some over there, and we'll come back to that, okay? So that's not as clear cut. On this N2O5 though, the only place that's showing is in the products of this one. So I know that I need to leave this one the same, and that I need to multiply this one by 2 because I need to have 2 of them. So So I'm going to come in here, and this one is going to have to be multiplied by 2. So I'm going to say 4 of those, and then 2 times that 1.5 is 3, y'all. Okay? 3 and 2 of those. Now, let's look at that oxygen again. See how I have 3 over here? That's like 3 little cars that match. And I have 2 little cars that match. I can pull out 2 of them. See? So let me take you through this, okay? Alright, I'm going to play the matching game. I have 4 in O's. Right? And here's its match. I pulled them out. They ain't in there anymore. Okay? Then my oxygens, I have 3 here, and I have 2 here. So what that means is these 2 match. I can pull them out, and I'm just left with 1. Alright, that's what I was looking for. And then the 2 and N2O5 are right here. So basically, what's left after I play the matching game, 4 O2s, 1 oxygen, 2 of those, and that matches, and I'm done. Now, I'm done with that part. What I have to do now is this enthalpy has to be multiplied by 2, and this enthalpy has to be multiplied by -2, because I reversed it and doubled it. How's that? That's not the worst thing that ever happened, right? So let the computer do all that pretty math for you. And that's Hess's law. So, cool. See? Times it by 2, times it by -2. And that's why. Let me do one more. Alright, so just take it one element at a time. And I'll tell you something, this is mean, but sometimes they'll give you reactions you don't even need. You know, I play this little game and I try to match all that stuff up. Sometimes they'll give you like 4 reactions and I'll only do like 2 of them. So I'm going through here and I'm like looking for stuff. Okay, so just know that sometimes you don't need all the reactions they give you. Okay, so carbon, I'm looking for carbon. Let's do one at a time. Carbon, 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 carbon. Oh, that's the only place with carbon. What do I have to do to this reaction? I have to times it by 3. I have no other choice. So, times 3, times 3, times 3, times 3. Right. The hydrogen, I see some hydrogen here. That's the only place. So what do I have to do to that first reaction? Times it by 2. So that's 4, that's 2, and that's 4. Times 2. Alright? And then this propane here. Propane and propane accessories. The only place that I see propane is in that second one, right? And it's backwards. It needs to be on the product side. So I'm going to reverse it. So I'm just going to take my pen here. I shouldn't have done such a good job. I can't see what I did now. Redo. So I'm going to rewrite it. I'm going to line up my yield signs the best I can. I'm going to write like right here. So 3 CO2s. And also, I see I have 1 and I have 1. I don't feel probably like I'm going to need to multiply or anything. See what I'm saying? Okay. So 3 of those propanes. Just kidding. 3 of those carbon dioxides. Oops. That looks awful. I can't. I'm not going to sleep tonight if I do that. There. Sorry, people at home. Should came to school today. Just kidding. So 3 carbon dioxides and 4 waters. And like I said, the state symbols do matter because you can't cancel out like liquid water and gaseous water. You can't do that. Okay. I just don't have a lot of room. And so methane, propane, and oxygen. So now let's take a look and see if we need to do anything else. Playing the matching game. So first of all, let's see, hydrogen. I have 4 hydrogens here, and I wanted 4 hydrogens, so cool. This oxygen, I have 2 oxygens here, and there's 3 of them, and I have 5. See, I have 5 cards and 5 cards. Da-da-da, da-da-da, da-da-da. Okay, cool. That water, I have 4 waters on this side, and I have 4 waters on that side. That's gone, right? We got rid of that. And then I have 3 carbons, and I wanted 3 carbons. I have 3 carbon dioxides, and 3 carbon dioxides, and all that's left is what's showing. So this one has to be multiplied by 2. This one has to be multiplied by -1, because I flipped it. And now it has to be multiplied by 3, and you're going to add them up. I made up that matching game thing, by the way. I guess your book didn't talk about it like that, did it? Sad face. Do y'all need to try one of these? Like just one maybe?
These are easy, right? Well, you're like, yeah, it's easy. Huh? So go ahead and do, like, real quick, if you want to give one a try, try out, oh, we're good on time. Compared to last year, we're doing great. I've closed up my practice problems. Can y'all show me one? Thank you. Go back to the practice problem. I'm going to tell you which practice problem to do. You're in the PowerPoint. Good stuff. Scroll down. Alright, wait, back up. Why don't y'all try, I mean, number 5 looks kind of easy. Y'all try like number 7 since it looks like a pain in the butt. 7 it is. Oh, here's mine. It was opened up the whole time. Thanks, Jalil. Sometimes you have to multiply by fractions, by the way, or divide. Same thing. Divided by 2 is the same as multiplying by half.
How's that going? You don't do the match yet part, okay?
So even though it's along the NO is on that side, you still have to switch it to the different potential. Like first equation.
The first equation?
Yeah.
Yeah, I have to switch that one because this knife, you know, I need this one to be like that, right? That nitrogen oxygen has to go away. So the only way to really accomplish that is to put this first one. That's really why I did it. That was my logic. The 156 in my head. No calculator. Okay. Is there any of this that I need to like talk to you about? Yes. Because I have to have one. The only place that shows up is here. And so I have to multiply that whole equation by half because I can't make it any other way but one. Half times 2. It has to be this. So whatever coefficients are up here rule what you do down here. So what I do, and I just did it, is I take it one at a time. One at a time. And if you just go stepwise to those 3, not worry about, don't look down here, look up here. You know what I mean? It goes a lot faster. I know y'all started working. So, this is something you have to practice. But I just like, okay, what do I gotta do for this? What do I gotta do for that? What do I gotta do for that? Don't worry about like the nitrogen and oxygen thing where I knew I had to cancel. That kind of took care of itself because I was paying attention to other stuff. But if you'll do it that way, it's a lot faster. How do you feel? Enough to do that one on your own? We have one more time. Everybody hates me. Any questions before I make this go away? This hot mess go away. Some of y'all are still right. So what's going to happen on Monday? That lab is real quick. It's not a big deal. All right. You have to do math with it when we're done. It's a lot of fun. And then Tuesday, you know, all this. I'm not like after today. I don't have anything else to teach you. Tuesday we'll kind of wrap up some loose ends. I'll let you look over the quizzes that we already took. Go over some of the release exam questions, and you can have time to work on some of this that you haven't finished. But the bottom line is, if you don't do a lot of homework this weekend, you're going to drown or fail next year. Not next year, next week. The next 5 days of your life. Not next year. Like very soon, you'll drown or fail. Like those 2 things will happen. Or one of them. Or both of them. Maybe both. Yes, ma'am.
I got your answer, but I just have to do it all at once.
Yeah.
So
It's like you can do however you want. I'm kind of lucky because I can write over mine. So it does. If I don't have this ability, I do have to rewrite things, and that's okay. What I do if I have to rewrite stuff, you see how I mark it out and then write it below and then write it below. That's the best way to, or the fastest way I find. So, is there any questions though for me? Cool. Last way. The last way is easy. Is sort of, and it has a formula on the formula sheet. The only thing is, don't get confused with what we did yesterday, right? No formula sheet for that. So here we go, sweet children. Party time. I say that. I don't know if I mean it. There we go. Alright, so enthalpy of formation. Here's the thing. We've been doing enthalpy, and it's just been delta H. Alright? Now, this F right here means formation. And so, when you have this little not sign, that little 0, that means at standard states. So at standard state for thermodynamics, which is not the same as STP, can't make this stuff up. Standard state for thermodynamics is 25 degrees Celsius. So should I convert everything to Kelvin? No. 25 degrees Celsius and 1 atm. And that's different than STP, which is 0 degrees Celsius and 1 atm. Because you know, it's not hard enough. It's not easy. It's not hard enough to learn one thing. You have to learn everything, right? So
That's, if you look on that formula sheet, look on the formula sheet, it has a little F on it. That's how you know this is not the other one. So the enthalpy of formation equals the sum of the products enthalpy of formations plus the sum of, minus the sum of the reactants enthalpy of formations. That's on your paper. Do you see the formula? It has a little F on it, yeah? That ain't what we did yesterday. There's no F? I doubted my life for a second, and then I quickly realized that it wasn't my fault. Alright, so anyway, I feel like I skipped a slide and it was really important. Yeah, listen to me, look. The enthalpy of formation for anything at its standard state that's an element. So I'm saying at room temperature, basically, if it's an element or if it's in its elemental stage, its enthalpy of formation is 0. So like all these metals that are just solid or gases, so like the Brinkelhoff guys with the L or Cl2 and H2, all these guys, that's their standard state at room temperature. Like chlorine is not found standard Cl minus or whatever. So also the enthalpy of formation for hydrogen ions, like for the acid, you need to write this down, is 0. That's the only other, all the other ions, as far as I know right now, they have a number. Like when you do your pre-lab questions, the enthalpy of formation of sodium ion is a number, not a 0. But when you do that number 1 on your pre-lab, where it's an acid-base neutralization, that H is 0. So anyway, aqueous, right? Cool. Alright, so now let's do some of these. Woo! Oh, here's the formula. The enthalpy of formation, or the enthalpy of a reaction equals the, this just looks awful. Basically, whatever, can I just do it? That would be better. Don't look. Burn your eyes, children. Oh my God. I can't even make that okay. Alright, here we go. Let me just cover that up. I do need to scooch it down just a hair. Stop looking. My eyes.
I see why.
Okay, here we go. So basically that formula is saying the enthalpy of reaction, okay, is equal to, means sum. I gotta add all that up. You know in sigma notation in the math class? Yeah, you just gotta add all this crap up and then minus all that other stuff, okay? So, anyway, it's products first, which is cool because you got a formula so you don't have to remember it. So, I'm gonna have to take 2 times, I'm doing products, right? You see why? 2 times the enthalpy of formation of iron, because I got 2 of them, right? Plus the enthalpy of formation of aluminum oxide. And I just have one of those, so no biggie. Then I have to subtract all of this stuff added up. I gotta do the same thing for the reactants. So one of these, and I'm just gonna, it's times 1. And then plus 2 aluminums. I ran out of room. 2 aluminums, okay? Now that's not the first thing that happens. You just go on. So now, where do you get the enthalpy of formation on the AP exam? They'll give it to you right above the question. So you don't have to have this memorized. But now we gotta look it up. So I told y'all to get the book out, and that's why. So on aluminum oxide, I'm looking in my book. The enthalpy of, hang on, let me start. Delta H equals the sum of, what's iron as a solid? What's its enthalpy of formation? How about 0? Yeah, 2 times 0 kilojoules per mole. And these are kilojoules per mole, whatever. Okay, good. Plus the aluminum oxide. I just have one of those. And it's, I'm going to round to the nearest whole number. So 1676. Negative 1676 kilojoules per mole. Alright, so I gotta add that up, and then I'm gonna subtract all of this added up. Iron oxide, go to the iron part. This is a lot of fun, right? Having a party up here. Make sure you pick the right iron oxide. Also, like when we get to water as a gas is different as water as a liquid. So, you gotta be careful, okay? So Fe2O3 is what I'm looking at, and I found negative 824. Y'all got that? So negative 824 plus 2 times, and guess what aluminum is? Is 0. Cool. So all of this is just 2 times 0, so that's 0. So negative, it says, this means I gotta add this up. So negative 1676 kilojoules per mole. And then I gotta subtract what I'll get when I add that up. That's what that crooked E means. Somebody said that to me. That really happened. Negative 824 kilojoules per mole. Have you seen this math trick yet? If you don't know that one, I can't help you. Let's see what I meant. Okay. So negative 1676 plus 824. And you get negative 852 kilojoules per mole. Now I know that wasn't that bad. This is actually like the easiest thing. True. But it just looks like a hot mess. It looks so scary. You're retired. I got the same answer. That looks terrible. Do y'all need to try one of the? Y'all want to try this one real quick? Do it to it. Hurry. This one. You don't know where to write this? I have some notebooks back here. I'm going to quietly work this out up here while y'all work it out. Be careful that you're using the right states. Water, gas, water vapor, not same as water liquid. Okay? And I am taking time to write all this out, but that's because I've screwed up enough of these to know better. Water's under oxygen in your book. I'm not even kidding you. I say that, I can't find it. Oh, there it is, as a gas. The hydrogen sulfide is probably under sulfur. It is. This is where you hope for elements. Like, yeah, come on, oxygen as a standard state gas. That's the nerdiest thing I've said today. What are y'all looking for? Did I mess up? Did you figure it out? What are you looking for? Hydrogen sulfide? Show me what you're looking for. So, sulfur dioxide? There it is. H297. SO2.
Oh, you switched it around.
Well, same thing. Don't matter. Sorry, July. formation for the products. And that's when I got to the sum of the enthalpies of formation of my reactants. And now I'm doing the little magic trick. That should come out to negative 1,036. Hey.
I can do it. It just takes me 30 minutes to find the thing.
It's okay. I kind of told y'all where to find it. It's under like the main element. It's on the AP exam. They'll give you a chart. Don't worry about it.
I found it the second you said it, but I wasn't there yet, so
Okay. All right. So y'all have about 2 minutes or 3 minutes. So listen. Let me tell you how to do this. The pre-lab questions are just like this. So your pre-lab questions, you're going to use the net ion equation, hydrogen plus hydroxide minus sign gives you water. That's you're going to find the enthalpy of formation of that. Then you're going to find the enthalpy of formation for sodium carbonate, gives you sodium, 2 sodiums and a carbon. Then sodium bicarbonate gives you a sodium and a bicarbonate. And if you can't find some of these in they're in your new book, the old book will have them all. But you can use the internet. Those are so that's real simple. 3 of these problems, okay, is what you have to do. And then on Monday we're going to do the calorimetry, and then we're going to compare the answers, and it should be the same. It's going to be fine. Remember, this was the easiest year, remember? Bryce said that. Yeah, okay.
If you're at home today, I hope you're still awake. Have a nice day. Have a nice weekend. You have a lot of homework to do if you're at home. Skip number 15 through 17 on the second thermodynamics.
I might go home.